Welcome to today's recording of an introduction to F#. My name's Glenn Stevens and I'll be your instructor for today's session. And just a reminder to make sure you download the course materials for today's class, as we're going to have a lot of fun with a mixture of lectures, exercises and quizzes. Alright, let's get started. So we have 3 objectives to achieve today. We'll cover why F# is important, how to work in the REPL, and the basics of working with expressions and loops in F#. So by the time you've completed this course, you'll know your way around F# syntax and features and be on your way to mastering F#. Now let's get started. We're going to start with some basic information about F# and hopefully show you why so many people are excited about the language. And we have a few tasks for this objective: to briefly cover the history of F# and functional programming, to show why immutability is such a useful feature, to go over some of the more advanced and fascinating features of F#, and finally to talk about several of the benefits of F#. So let's first back up to the very beginning and answer the question, what is F#? And F# is a modern functional language designed for the .NET platform. And it was created by Microsoft Research and has been around since 2005. And we're going to primarily compare it to C# as we go through this course. And it has quite a few differences, which you can even see by looking at these 2 code fragments on the screen. So F# is clean and efficient. There's no need for all those curly brackets. In fact, the lines of code count is significantly less on F#. There's 3 lines of code, where on C# there's 12. On F#, the boilerplate code is super minimized, and it's functional first. So in terms of language features, F# is a superset of C#. So everything that C# can do, F# can do just as well. But the opposite, however, isn't true, as F# has a number of features that C# isn't capable of, as you'll see. And in addition to that, it's important to remember that F# is a CLR-based language, and once you compile it into an assembly, it can be used by any other .NET language, such as C# or VB.NET. And that means you can select F# for certain aspects of your application and continue to use a more traditional OO language for other parts. And the history of F# as a language starts with Dom Syme and many others at Microsoft Research in Cambridge. And it started life as an academic research project, and over several years matured into a production-ready language that's used by many commercial companies, especially in the financial sector. And Microsoft actually used it to develop portions of the MSDN website, which is one of the reasons it became an officially supported language. The history of functional programming and the roots of F# begin back in the 30s, when lambda calculus was created. In 1973, the functional language ML was created. It's not the first functional language, but it's the one that F# is based upon. In 1996, a derivative of ML that added object-oriented features, OCaml, was created, and in 2005, Microsoft Research took that OCaml basis and created F#. By May 2010, F# was included out of the box in Visual Studio. In November 2010, F# was open sourced. And in the last year, F# has released version 3.1, as well as being included out of the box in Xamarin Studio, which brings us to this course. We've seen a short history now, but before continuing, we should pause to consider we haven't actually defined functional programming. And most of you from the C# world were introduced to functional programming with LINQ, even if you didn't actually realize it at the time. So consider the variable numbers here. We're taking the set of numbers from 1 to 10, then filtering that set. The output from that filter is sent to the toList method, and now since it's a list, we can call for each, which is a method of the list class. This will execute the pass lambda expression on each of the values, which will then print the numbers out to the console. And this chaining style of programming is the essence of functional programming, where the output from one method is passed directly into the next to generate our final result. We can continue chaining methods in this fashion as long as the inputs for a certain method match the output for the previous method. And in many cases, we work on the data as it's produced, saving memory and allow us to provide a stateless style of programming where no information is stored. Think for a minute about the expression x equals x plus 1. As programmers, this is something we do nearly every day, and we call it increment, right? And it's one of the first things we learn in our classes. But what does that mean in the real world? What would your childhood maths teacher have said about this equation? In math, it's actually just wrong. Solving this equation for x isn't possible. X can't change in the real world. It has a single value that can be determined at any point. And if X changes, we can't pin anything down. And it's actually very difficult to make sense of anything. Consider not just simple incrementing of values, but also independently modifying data. In the following bit of code, we're multiplying two numbers, or two integers. But later in the code, we update one of the numbers that we use. And the value for C is now different at different points in the code. So while the value for C may have originally been valid, it's no longer valid once A has been updated. And this style of code can create side effects and bugs which are hard to identify and reproduce, which also makes them hard to fix. The solution to these issues we've just posed is immutability. Immutability by default is one of the key features of F#. It simply means that the values can't be modified once they've been assigned. And this simplifies code immensely and provides three key benefits: parallelization, performance, and predictability. Let's cover these in more detail. First, let's look at parallelization. So are there specific times where parallelization is particularly desired? Well, GUI-based applications, particularly mobile apps, must remain responsive, which usually means using multiple threads. And when we work with multiple threads and shared data, there's always the possibility of a race condition. For example, let's look at a simple case of incrementing a counter being accessed by multiple threads. So there's a thread that accesses the counter to read the value. It then adds 1 to the counter. Then a second thread comes along and reads the current value of the counter. Threads 1 and 2 now agree that the counter value is 1. Now, threads 1 adds 1 again, but so does thread 2. At this point, what should the counter's value be? Now both threads 1 and 2 say 2 because each added 1 to 1, but really it should be 3. Parallelization is a really hard problem, and adding shared mutable state to that can actually make it nearly impossible. In F#, because of immutability, the threads aren't arguing over a common shared value. Unrelated functions can execute in parallel without an issue because they don't need to worry about ordering or whether one function will change the result of other functions. And eliminating shared mutable state makes the problem of parallelization much easier and solves the most common sort of bug that we find in C# parallel programming. Back to performance. And it turns out that having immutable data provides for several interesting performance benefits. And keep in mind that performance is a shifting target, and that depending on the code structures, the machine architecture, and the features that you use, you can get different results. First, the just-in-time compiler can produce more efficient code and perform aggressive caching of values. And this is primarily useful with parallelized code. Second, and more important, it makes your code cleaner, and the lack of required synchronization means you don't have the bottlenecks that are often produced by locks and monitors in shared state. And finally, as you'll see, we can more easily parallelize our code with F# as it has several really nice features baked into the language and libraries. This means it's more likely that you'll use it and get a potential performance boost on multi-core CPUs. As an example, consider 10 million hash inserts on 3 functional .NET languages. All 3 are running the same CLR with the same just-in-time compiler, but the F# code tends to generate slightly more efficient code, which requires little to no synchronization and therefore increases the performance of the code dramatically in this case. And as a subsection to performance, I want to mention pipelining. Remember when we talked about link? We said that because no information was stored, it was possible to chain methods together as long as the inputs for the current function match the outputs for the previous function. And F# has this same concept, and it's called pipelining. And if you've done any Unix shell scripting before, the concept should be familiar. It's also a lot like building with Lego. They're all composable and fit together nicely. And pipelining is an important performance feature because with it, we're able to process data concurrently, which gives us our performance advantage. Immutability also has the benefit of being predictable. When you know that your values can't change, you have much more faith and confidence in your code. F# also has several other features that we haven't discussed yet, such as type inference and type checking, that just ensure that your data is being used correctly. So let's talk about some of the key features in F# that you don't find in C#. And first up is type providers. Have you ever wanted to write a class to read some data stream and turn it into an object graph so you can work with the data in a type-safe fashion? So it's you and every other programmer on the planet. And this often involves doing things like setting up a connection or opening a resource, obtaining and reading the data, creating the objects, and then consuming the data from the objects. And F# has this capability built into the language, and it's called type providers. And a type provider is a mechanism to provide types for the data that you're consuming to the compiler. Along with that, you get complete type safety and full IntelliSense, as you can see here on the slide. And with type providers, we simply connect to the data source. In this case here, it's a CSV file. And then we get IntelliSense and tooltips available for the data. We get no code generation. It's always in sync. It's scalable to millions of types. And it gives you exploration and early feedback on the data before compile time. And F# has type providers for all kinds of data, and you can write custom providers for your own data that fit naturally into the language. So there's plenty of them available, like WSDL, Link, XAML, SQLite, OData, as well as Azure Data Storage, and many more. Another great feature of F# is the ability to classify units of measure. This solves another common source of bugs in programs where we're converting or misusing data because of the assumptions as to the type of values being consumed. And a great example, you can actually see that on the slide, is the Mars orbiter crash, because it used English units where it should have been using metric units. There was confusion about the different types of units of measurement. So in F#, the unit can be any string, like pixel, to distinguish space on the screen. And here on the slide, you can see decorations applied to values to ensure we also know exactly what kind of data and what unit it's in. And this is enforced by the compiler, and it even does conversions when passed into methods expecting a different unit. For example, if I passed in a length in centimeters and the method expected inches, F# can perform the conversion for me. Here's another cool feature of F#, discriminated unions. These are named values in a closed set, and the closest feature you've probably used in the past is C# enumerations. But F# discriminated unions are much more powerful. As an example, consider the dimmer switch that's shown here. The switch value can be on, off, or a floating value based on the slider next to the on-off switch. Modeling this in C# is messy and awkward. You could model it a couple of different ways, but you'd risk runtime errors in one, a maintenance nightmare in others. And with F#, it's a piece of cake because I can have discrete on-off values and then add in a floating point value to track increments. And discriminated unions can also be useful for modeling simple object hierarchies. In C#, you might need several files for a base class and several associated child classes. But in F#, you can avoid that class explosion by having just a single line of code to model the same information contained in each class. Okay, so we've seen some cool features unique to F# and talked about some specific design decisions the F# team made in creating the language. Let's talk about what all this gets you. First, F# is declarative, and that means you code for what you want to have happen, rather than how to perform the operations. F# then provides the functionality to complete the task. And this approach means we avoid many of the side effects that you get with imperative languages. And F# is not a purely declarative language. It allows you to mix in imperative style programming when necessary, particularly if it interrupt with other languages like C#. But it's a big step forward. And as you've seen, F# code tends to be easier to read. And we're going to call this simple. However, you might not find it simple when you're first starting out. But as you'll absorb the language and learn the F# way of doing things, you'll see how much easier the code will be to create, to maintain, and also to understand. F# is also very concise. We don't use a lot of the language placeholders that you find in C#, and much of the boilerplate code that you end up writing to create custom types and algorithms are unnecessary in F#. Finally, as a result of all these, F# tends to be very productive. And this is the main reason so many programmers learn F# and never go back. They can get so much more accomplished in the same amount of time. So let's do a quick flash quiz. Immutability means that values cannot be changed once they're assigned. True or false? And the answer is true. Functional programming is based on A, differential calculus, B, Lambda calculus, or C, fractional calculus. And the answer is B, lambda calculus. Functional programming is a style of programming that models computations as the evaluations of expressions while avoiding what? Is it bugs, class, or state? And the answer is state. So we've looked at many things about F#. We've looked at the history of F#. We've described what functional programming is. We've looked at the important concept of immutability, and we've identified some of the advanced features of F# and looked at also the benefits of using F#. Let's move on and actually run some F# code to give you some practice with the language. And our goal here is to work with the F# REPL environment in Xamarin Studio or Visual Studio. Let's start by defining what a REPL is. And a REPL might be familiar to you if you've worked with Visual Basic back in the day, or from any of the several languages today that have a REPL. So C# even has a few online REPLs. There's tools like LinkPad, which is a REPL, and also Xamarin UI Test has a REPL. And essentially a REPL is an interactive environment where I can type statements in and get an immediate response. And REPL stands for Read, Evaluate, Print Loop, because that's exactly what it does. It reads your input, evaluates and executes it, prints the results, and then you start over. Both Xamarin Studio and Visual Studio have a built-in REPL environment for F# where we can type in F# statements and expressions and get immediate feedback from the compiler. And you access it through the View menu. Once we have our REPL window open, the simplest thing and perhaps the most common thing we'll do is assign values. And we do this with the let keyword in F#. And notice that I use the term values and not variables. And this is because F# values are not variable. Once they're assigned, they can't be changed by default. And you can see three examples of assignments here. The first assigns an integer value 10, the second a double value 20, and the third a string. And notice that we don't define the type of storage. That's always inferred by the assignment itself, kind of like the var keyword storage type in C#. When you do anything in F#, you'll always have a return value of some kind. If there's no calculated value from the statement, then the return value is inferred to be unit, which is essentially a void return. However, F# still considers this to be a value. As an example, let's look at the code. We've got two things happening here. First, we have an integer assignment 42 to the value x, and this has a return value of int equals 42, as you can see. Next, we are using the built-in function printfn, which outputs formatted values to the console to print out the value of x. We can see the output followed by the result from the method, which is unit equals and then an open and close parentheses. And this represents no value being returned from the method. And you just saw the usage of printfn, so let's have a look a little closer at it. And it's a built-in function that's used to print text and formatted data to the console along with a new line. Now, similar to the console write line. However, the format strings you use to output the data are quite different. In fact, it actually has more in common with the older C function printf. And here you can see some examples of the output. %s for strings, %i or %d for integers, %f for floats, and %b for Boolean values. And MSDN has a full list of the format specifiers you can refer to. The important thing here is that F# will validate the parameters at compile time and ensure that they're the proper type, unlike console write line, which just blindly outputs the values it's passed. And this provides for much better type checking on your output. And there are other methods you can use as well. Printf outputs to the console without a new line, bprintf outputs to a string builder, eprintf to the error console, and fprintf to a text writer. So we're about to use the REPL to type in some F# code, but here's an important tip for you. When you're trying out some new code, you'll often want to clear out any previously entered values, kind of like clearing a calculator before starting a new equation. And you can do the same with a REPL by either right-clicking and selecting Reset, or using the toolbar buttons. And the screenshot shows Xamarin Studio, but similar options are available on Visual Studio as well. Now it's time for an individual exercise. Open the starthere.html document and select the first exercise, which is really just an introduction and slight exploration of what you can do with the REPL. Now pause the video at this point, and when you finish the exercise, you can resume the video. Now, the purpose of this exercise was to really get a level of comfort with the REPL. And in order to bring up the REPL, from the View menu in Xamarin Studio, we select Pads, and then we select F# Interactive. And that will open up the REPL. You can see the REPL down the bottom here. I might just move that up a little bit. And here I can enter some statements or enter some commands as well. So I might use the printfn, hello from F#, and then I'm going to use a double semicolon. Now F# doesn't use semicolons, but in the REPL it uses the double semicolon to tell it to execute the current block of code that you've entered in. So I hit return there, and there I can see the hello from F#. I could also assign some values. Let x equals 10, use the double semicolon, and have that block print out as well, or display the values. I could create some other values as well and execute those too. So the REPL is a great tool for entering and seeing how your flow of logic will execute over time. Another great tool is sketches. So if I select File, New File, and I select F#, and then I select the sketches, I can create a Xamarin Max sketch. I'll enter the name, exercise 1, select New, and sketches is essentially a REPL too. I can do the same things here. I can assign some values. And then see how they'll execute over time. So certainly a great REPL tool to use as well. Okay, now you've done a simple assignment, let's just make sure we have some sort of basic syntax rules covered. And first up, we'll look at F# comments. And F# supports both single line and multi-line comments. And let's look at the language rules, and especially the case sensitivity. And F# is a case sensitive language, just like C#. And you can see examples here. We've got the let name equals Helen, and even the capital L on the let. So keywords in F# are all lowercase. Although that looks a little bit like Visual Basic, it's all lowercase keywords for F#. Now we've also got 3 different declarations at the bottom of that slide too. Let name equal Helen, let name with the capital N equals Mark, and let name all caps equals Rachel. So they're all perfectly valid, although it's a little bit of obfuscation being done by hand, but you want to be aware of those kinds of things too. And F# doesn't use statement terminators, although as you've seen, the REPL uses them to terminate a block of entered code and then begin executing it. And here's an interesting example which will trip you up as you transition from C# to F#. And F# doesn't use commas to separate parameters past the methods or functions. Instead, we use spaces to delineate parameters. And here you can see we're calling printfn to output 2 values, but you'll notice the space between them. And one important piece of code I want to point out here is the assignment for number. We're actually using a new random object from the system namespace. And you'll notice that we new up the instance and then call next to get the integer value. In order to create the random and then call next to assign to our value, we must surround the creation in parentheses. And this ensures that F# evaluates this properly. And generally, anytime you're calling a function to get a value in line and are using it as an intermediate to get to another value, you'll need to use parentheses to enforce the ordering. Now let's have a look at how multi-line statements are done in F#. And whitespace is really good, especially in F#. And in fact, in F# it's necessary. So if you've used a tool like stylecop, which forces proper indentation, amongst other things, in the name of best practices, you'll actually find F# pretty comfortable. In F#, we just automatically enforce the best practices.
There's a lack of curly braces, which makes for cleaner, easier to read code at a glance. There's a lack of boilerplate code. And as you can see here in the sample on the slide, we define a new function named evens, which takes a list of integers and returns only the even numbers. We use spaces to push the body of the function definition under the assignment, and this is how F# knows the code to associate. For comparison, you can see the same function implemented as C# using a link expression. And this use of spacing will also trip you up at different points, particularly if you don't align them correctly. And here on the screen, you can see some code which will fail compilation because the A plus B is not properly aligned with the preceding statements. And the previous line is not a proper expression where the alignment would make sense. And the correct code is shown here where all three statements are aligned. And ultimately, you want to make sure that you turn tabs into spaces in F# and set an appropriate spacing. And most people will tend to use 3 or 4 spaces. Now, F# is a fully compliant CLR-based language, and as such, it uses the common type system. And that means it has all the same C# types. In fact, big integer actually made its debut here before being put into the .NET formally. And as mentioned earlier, F# uses type inference to determine the type based on the assignment, and that means everything must be assigned to a value. And here's an example of the type inference in action to assign an integer value. Even when we define functions, F# uses the surrounding information. The fact that we assign integer values to decide what the input parameters are, in this case it turns the square function into one that takes 2 integers. And when you change the type, F# reacts accordingly. Here we're shadowing the square function with a new value that takes floats. When using type inference, sometimes F# gets it wrong or can't figure it out based on surrounding information. For example, here we have a new person class defined that has a method on it called sayHi, which outputs the name to the console. And when we go to use that in a function that takes a list, F# will not correctly infer that we intend it to be a list of person objects, and therefore won't allow us to invoke the sayHi method. Instead, it generates an error. And we fix that by applying a type annotation to give F# a bit more information about our intent. And here we tell F# that we're iterating across a set of person objects. Because we use type inference, it's a good idea to understand how to define particular types in F#. And if you look at the tables on the slide, you'll see the C# keyword and how to actually assign that particular type in F#. For integers, you see that we'll just use the whole numbers. For doubles, we'll use the dot after that value. For floats, we'll use the .f. For big integers, we'll use the .i as the suffix. For long, we'll use the L, and for the ulong, we'll use UL. And you can see the other formats for shorts, ushorts, bytes. For strings, we just wrap the values in quotes. And just in case you're wondering, operator overloading is supported in F#. Let's look at the maths operators and see how they differ from C#. You can see the addition, subtraction, multiplication, and division. There's no real difference there between F# and C#. You can also see we have the integer modulus, that's the percentage sign, and the exponent or power is the double asterisk. The less than or equal, greater than or equal to remain the same for F#. But for comparison values, we actually use a single equal sign rather than the double equal that you'd be used to in C#. Likewise, for not equals, we'll actually use a less than followed by a greater than sign. We still have the Boolean or and with the double pipe or the double ampersand. And there's also the bitwise operators if you need to use those. And the default for any assigned value in F# is to have it never change, i.e. it's immutable. However, when you're building GUI programs, mutability is inevitable for UI state, and so F# allows you to decide to make certain values changeable by applying the mutable keyword when the value is assigned. Here you can see an integer x being assigned a mutable value of 5, and then we're changing it to 10 later on through the assignment operator. The assignment operator is a less than followed by a dash, not an equal sign. And only values that you explicitly make mutable can be changed this way. And you should prefer to use immutable data if possible, but F# allows you to relax the rules when necessary to get the job done. Now it's time for another individual exercise. From the Start Here document, select the second exercise, which will be an example of working with mutable and immutable data. Again,
pause the video at this point, and when you're finished, resume the video, and then we'll review the exercise. And in the last exercise, we had a value that we appeared to have changed, but it was actually really another block of code. Now, to really create a changeable value in F#, we need to declare a value mutable, which means it's a variable. So let's define that in the REPL. Let's use the let keyword, and then we'll follow that with the mutable keyword and specify x is equal to 20. And we can then change the value for x by using the assignment operator, which is the less than followed by the dash. Then I'll execute that block of code. And you can see x is now 100 at the end of that block, which is expected. So now let's reset the REPL, and we'll declare some different types. I'm going to declare the num, which is going to be an integer. Just set that to 10. I'll define some text as a string, and I'll just put F# rocks. I'll also define a float, upper amount equals 42. I put the full stop there to indicate that. And I've also got another variable called hasLeft, which is a Boolean, and I'll set that to true. And then after I have all those values, I'll use the printfn function to just write out the values. And remember that the printfn function has strict typing, so it needs to make sure that the types in the parameters actually match exactly. Otherwise, we get a compiler error. So here I'll put the values are %i for the integer, %s for the string. I'll use the 0.2f for the floating point value, and %b for the Boolean. And then I use the F# convention of using spaces as parameter delimiters, and then write them out. So here we've got num, text, upper amount, and hasLeft. And I should be able to execute that block of code. Excellent. So let's do the last part of today's exercise, and we'll reset the REPL, and we'll define some values here. So let's define x equal to 10, which is going to be an integer. Let y is equal to 20, and we'll just define those values. Now let's add x and y together. And we can see that because they're both integers, they add together really nicely. But let's add a third variable into the mix, z. But z is going to be a floating point. And then after I've done that, what I want to have happen is add x plus z. Now they're two different types, so it actually is not going to work. So instead, what I need to do is I need to change that. So instead of having x plus z, I need to make sure that I do an appropriate typecast. So I might have to typecast x to be a float or z to be an integer if I want to add them together. So let's change x to be a float and then add that to z. And that works fine. You can see both z and the result are both floats. Or we could do it the other way. I could have x plus an integer version of z. And that's our second exercise, just recapped. So let's continue now with another flash quiz. Okay, question 1. You'd use which keyword to specify a value that can be changed? Is it alter, let, or mutable? And the answer is mutable. Question 2. F# types are not what, they are what. And the answer is F# types are not declared, they're inferred. And question 3. Printfn can be used to display A, a single value in a string, B, any number of formatted values in strings, or C, a console write line type of formatted string. And the answer for this one is B. It's any number of formatted values and strings, just like we did in the last exercise. So that brings us to the end of this objective, where we've had a look at what is a REPL, how to use the REPL in our IDE, and to create and display values and variables in F#. As a last topic, let's look at some common programming tasks such as evaluation expressions, branching, and loops. And we have three things we want to focus on. First, we'll look at some basic syntax rules in F#. Then we'll learn how to evaluate expressions and conditionals, and we'll finish off by understanding how to build loops. Expressions in F# are everywhere. In fact, almost everything you do in F# actually provides a value you can evaluate. For example, examine the code on the screen. It's not necessary to completely understand it yet. It's defining a new type called product that has a constructor that takes three values: name, price, and on sale. It then defines three properties: name, is free, and sales price. And the interesting thing here is that the sales price property is being set to true or false using an if-then-else expression. Now, unlike C#, which would only allow evaluation of the expression body or require use of the ternary operator, F# if statements return a Boolean result. So let's look a little bit closer at the if-then-else statement. Here's a few more examples using if-then-else to evaluate a condition and then provide a result back to an assignment. And you can also use it in the more traditional fashion as shown in the evaluate function being created here. It takes a myArray parameter and the body uses an if-then-else to print a statement to the console based on the contents of the array. In this case, the final result from the evaluate function will be the output to the console with the unit result code returned. And because everything returns an expression, it really opens up the ability to program in a functional fashion. In F#, we often combine functions and expressions fluently using a special operator known as the pipe operator. And take this code as an example. Here we're defining a random number generator function that takes a count of numbers to generate and returns a list of random doubles from 0 to 360. We then use that function to generate 200 numbers, average them together by piping the result list into the list average function, piping the average double result into the .NET sign method, and then taking the double result and then printing it out to the console. In C#, while we could use a series of link expressions, we would more commonly separate these into different statements with local state to hold the temporary values until we get our final result. And the F# syntax and model is more compact and concise, and once you understand the flow, tends to be more readable and understandable as well. Let's talk about loops. F#, as with most languages, has the ability to explicitly define loops in code and actually offers three different styles. First, the for in do, which is similar to C#'s for each loop. The for to do, which is similar to a C# for loop, and then while do, which is similar to the C# while loop. And we're going to look at three approaches, as these are certainly things that you'll often use in C#, and you can use the same programming style in F#. However, I want to stop for a moment and mention that when you really get into F# programming, you'll find that your reliance on loops will actually drop off as you learn the APIs for things like lists, sequences, and arrays. And F# has a whole set of defined functions that you can use to chain your logic, as you saw in the last code example, to where you implicitly loop across values, but don't actually use those keywords to do it. And we'll examine these features in depth in a future class, but let's look at the explicit keywords first, so you can see how the higher level functions work. The first loop is the for in do loop, which is essentially a for each style loop. And this is probably the most common loop construct that you'll use. And it performs a forward only, read only traversal of any enumerable set of values, processing each item with the expression body of the statement. And you can see the basic syntax on the slide. In the code, we loop across the values 1 to 10 inclusively and print each value out to the console. Our output will be 1 to 10 and the overall expression will return unit.
And the last point is interesting. All loops actually must return unit as a result. It's expected by the F# compiler. However, where the expression gets the value is from the final statement evaluated. So if we change our loop to instead perform an operation returning a non-unit result, as you can see here, then the result of the loop expression is actually int and not unit. And when this happens, the compiler will issue a warning indicating that the expression has an unexpected result, and even direct you to ignore the result of the expression to ensure that the loop itself returns the appropriate response. And to fix this, we use the pipe operator to push the result of the expression to a specific keyword, ignore. And this keyword will then return unit, which satisfies the loop requirements. Anything piped to this keyword is effectively thrown away and ignored. The next loop style is the for to do form. And this is essentially the same as the for statement, with some limitations though. It only supports forward traversal, so start must always be numerically less than finish. And the start and finish values must be integer, and it always must increment by 1. And here you can see a simple example where we define a counter function that takes no parameters. That's why we need the parentheses. And the implementation for this function is to go from 1 to 10 and print the result out to the console with spaces in between, then print out a new line at the end. And the final loop style we'll look at is the while do loop. And this is similar to the basic while loop in C#. And here we'll create an array of double values from 1 to 10 and then walk through that array, adjusting each array element to be the power of itself. And you'll notice that this requires a mutable indexer since we need to change it, and that it also points out that arrays are always mutable, unlike most other values that you use. Again, we'll cover arrays in another class. In this particular case, it might have actually been easier to use a for and do style loop, although we'd still need a mutable indexer since for and do just provides the values. Where you'll sometimes see this sort of construct used is when you're walking through input from a C# provider, such as an SQL data reader, where you need to check a Boolean to determine whether to continue processing. And beyond that, this style of loop is fairly uncommon in F# because there are better ways to do it. And we've talked about a few restrictions on loops already. There's no do while style loop available, although you can craft that style of loop in other ways. And there's also no break or continue support. And as mentioned before, for to do loops are far more limited than C#'s for loop. And ultimately, you can use these keywords to create loops, and sometimes you'll be forced to. But F# provides other mechanisms to solve these sorts of problems, which we'll examine in more detail as we begin to explore thinking more functionally. And let's review this objectives work with a quick flash quiz. Question 1. The for and do loop is similar to which C# loop? Is it the for loop, the for each loop, the do while, or none of the above? And the answer is B, the for each loop. Question 2. Conditional statements and loops return values in F#. True or false? And the answer is true. And question 3, to ignore a return value from an expression, you would use which of those 4 constructs? And the answer is D. That brings us to the end of the objective, where we've explored some of the basic F# syntax. We've had a look at how expressions work, and also had a look at some of the looping constructs in F#. So now you've got some of the basic skills and knowledge of working with F#. And this is the first in a series of 5 classes on F# with Xamarin University. So I do hope you'll come back and take the other 4. Certainly I find by the end of the 3rd or 4th class that people really get a strong sense of how to use F#. In our next class, we'll learn how to manage files and folders the F# way. And that brings us to the end of this introduction to F#. My name's Glenn Stevens, and you can contact me by emailing glenn.stevens@xamarin.com.
Thanks for watching, and congratulations on starting your F# journey.